So the plan for today, we're going to start looking at spring mass system. We'll look specifically at the unforced situation today, and then next class we'll look at a forced spring mass system. Just an application of these second order differential equations with constant coefficients. So the unforced systems will be homogeneous. It definitely won't take the whole class, so kind of take our time kind of describing what's going on, do a couple of examples, and then there'll be plenty of time to take questions that you might have if you're still working on assignment 3. I know there were a couple problems, 2 or 3, that were probably kind of challenging on that assignment. So we'll go ahead and get started. So the basic setup is we have a mass hanging on a spring. And as that mass hangs on a spring, there's a certain equilibrium where it hangs at. So that's x equals 0. X will measure displacement from equilibrium. So where it's hanging, that's our equilibrium. If it moves upward, that we're going to consider that a positive displacement, and moving downward as a negative displacement. Depending on the book you look at, they might flip those two, but you just pick a direction that's positive and one direction that's negative. So x of t will be the vertical position, and then of course its derivative is velocity, and the derivative of velocity is acceleration. And then we use Newton's second law, right? Mass is equal to force times acceleration, or sorry, force is equal to mass times acceleration. And so when we talk about the actual force, what we mean is like the resultant force, the sum of the forces acting on it overall is mass times acceleration. So that this mass times x double prime is equal to the sum of these forces. So F sub s is the restoring force. That's proportional to the displacement. So Hooke's law tells us that it's k times the distance, k times displacement. And it's opposite to the direction of motion. So Fs is negative k times xt. K is called the spring constant. And then we have a damping force as well, which is proportional to the velocity, and again acts in the opposite direction. B is called the damping constant. So Fd is negative b times x prime of t. So, you know, scenarios where we might have more or less damping, like imagine if it were submerged in water, then there's more damping, right? The faster it tries to move, like the more, the bigger the force is acting against it. And now, so our equation at this point becomes the following. Mass times acceleration is minus k times x of t minus b times x prime of t plus f of t, where this is maybe some external force acting on the spring mass system. If there are no external forces acting on the system, and in this section we're going to assume no external forces, then that f of t function is 0, and we have a nice homogeneous equation that looks like this.
Hello?
Yeah.
We can't see your notes or anything.
Okay, I am sharing them, so I think you have to go up to the computer at the front and like this happened before the break too at some point. And you should have like a hard copy of the notes there. Jason said he would go down and drop off like a pile. Does everybody have a set? It's just a thin little like handout. Okay, great. So we have this nice homogeneous equation, which we know how to solve. And depending on what that constant b is, what that damping constant is, we'll get different behaviors. So when we, if we were to graph x of t over time, we get different behaviors on what that displacement ends up looking like. So we've used these terms before: overdamped, underdamped, critically damped. So now we kind of have a context for what that means. So in this figure here, we got 3 graphs. They're just this homogeneous equation with different values of b for that damping constant. So in an overdamped system, this means that we've like sort of lifted it up initially and let it go. right? So that's why it starts off, it starts off at 0, we've lifted it up, we're letting it go, and then it kind of just comes back down to equilibrium right away. Critically damped comes right back down to equilibrium. And if it's underdamped, that means that there's less damping. There's not very much damping, so as you let it go, it just sort of kind of keeps going and then kind of gradually approaches that equilibrium. We're going to do a couple of examples together. And then there are exercises, like 3 or 4 problems posted. I think I remembered to post them. Yes, as a PDF. So we have a 1 kilogram object hanging on a spring with a spring constant of 4 newtons per meter. So that means the spring constant is K. The system is submerged in water, causing a large damping constant of 5 newton seconds per meter. We're going to find x of t, so we're going to find the position function, and solve the initial value problem if it is lifted up 1 meter and then let go. So there's 2 parts to this. In part A, we're just lifting it up 1 meter and letting it go. That means that at x of 0, at time 0, the displacement is 1. It's 1 meter up. We've lifted it up, we're letting the positive, moving it upward be the positive displacement. And it just lets it go. We're not pushing on it. We're not giving it, we're not imparting it with any initial velocity. We're simply letting it go, and that means that the initial velocity is 0. So here's our basic equation, mx double prime plus bx prime plus kx equals 0. And k is 4, b is 5, and m is 1. So that means we've got x double prime plus 5x prime plus 4 equals 0. And when we're solving a homogeneous, we use the same techniques we were using before the break. We're going to write down the characteristic equation. R squared plus 5r plus 4 equals 0. And I think that'll factor. Plus 4 plus 1. So our roots are -4 and -1. Yeah.
Is there supposed to be an x on the x double prime plus?
Oh, yes, yeah. Yes. Over here, you mean?
Yeah.
Yeah, sorry. So for folks in Randolph, John just said, is there supposed to be an x? Yeah, so this is 4x. I left off the x at the end. So we have 2 distinct real roots. That means that this is overdamped. And our solution is going to look like this. Some constant C1 e to the -4t plus C2 e to the -t. And now we want to find out what those constants are. So we can find x prime of t and use our initial conditions. So we have what? -4 C1 e to the -4t minus C2 e to the -t. And we can use our initial conditions. So x of 0 equals 1 means that 1 is equal to C1 plus C2. And x prime of 0 equals 0 means that 0 is equal to -4 C1 minus C2. I think right off we're ready to just add these equations together, use elimination by addition. we get 1 is equal to negative 3 C1, because the C2s will cancel. And then C1 is equal to negative 1/3. And that means that C2, see if I use the top equation here, if C1 is negative 1/3, C2 has to be 4/3. And we get our solution. Negative 1/3 e to the minus 4t plus 4/3 e to the negative t. How's that? We can, sometimes I think it's interesting just kind of look at what these look like. Kind of just map the, or plot the displacement over time. So, let's see, that's left over from a different, so we're going to graph y as a function of x here. So what do we have? Negative 1/3 times e to the negative 4t, negative 4x, plus 4/3 e to the negative x. Now, they said that we lifted it up 1 meter and just let it go. It's obviously not going to stray more than just 1 full meter from displacement. So I'm going to set this window to go from, I think I'll just go out 10 seconds, 0 to 10, and then the y to go from -1 to 1. We might not even need it to be that wide, but we'll take a look. So it gets lifted up 1 meter and then kind of pretty quickly starts approaching equilibrium. Doesn't really dip below it at all. This is an over-damped system. There's maybe a slightly nicer window to look at it. Questions so far on this? Okay. And then it says, what if we lift the object up 1 meter? So same scenario. If we lift it up 1 meter and give it a downward velocity of 5 meters per second. So we're not just letting it go, we're kind of pushing it downward after we lift it up. So that doesn't change our homogeneous solution, like the general, right? We're still working with x of t equals c1 e to the negative 4t plus c2 e to the negative t. It just changes one of our initial conditions. So it's lifted up 1 meter, x of 0 is still 1, but now x prime of 0 is negative 5. Again, x prime of t, I'm just going to kind of copy this over. Negative 4 c1 e to the negative 4t minus c2 e to the negative t. So x of 0 equals 1 means that 1 is equal to c1 plus c2. And x prime of 0 equals negative 5 means that negative 5 is equal to negative 4 c1 minus c2. Again, this is set up nicely to solve by elimination by addition, so we'll just add them together. The c2's still cancel. We have negative 4 is equal to negative 3 c1. So this time we get c1 is equal to 4/3. And that means c2 has to be, again, if I use this top equation up here, C2 has got to be negative 1/3. And this gives us 4/3 e to the negative 4t minus 1/3 e to the negative t. So a pretty similar looking function for our displacement. Maybe we'll take a look and see how that graph differs. Ah. Oh, okay. So it was given an initial downward velocity, which was enough so that once it was released, it kind of came back below the equilibrium point before it was sort of yanked back up again. I'm going to just adjust this window a little bit. Let me go down to negative 0.2, and I probably don't, I'll just go out to like 8 seconds. There's that one, and we can sort of look at the other one superimposed. So, you know, the damping constant can have a big difference, or not the damping constant, the initial velocity that it's given, right? That's what we're seeing here. Questions? Okay. All right, well, let's do one more. Here, this time we have a 10 kilogram mass suspended on a spring. They give us a spring constant at 20 newtons per meter. The damping coefficient is 30 kilograms per second. The mass is initially at equilibrium and given an initial velocity of 2 meters per second in the downward direction. Okay, so here's our basic equation. M times x double prime plus bx prime plus kx equals 0. We know that m is 10, so 10x double prime plus 30x prime plus 20x is equal to 0. Before we solve this, you know, this is an initial value problem. They tell us that the mass is initially at equilibrium. So that tells us that x of 0 is 0, right? The displacement from equilibrium is 0. And then an initial velocity of 2 meters per second in the downward direction. That means that x prime of 0 is negative 2. And we're going to find our function. So, I mean, the first thing we might notice is sort of convenient. All of the coefficients are multiples of 10, so I'm just going to divide by 10. We get x double prime plus 3x prime plus 2 equals 0. And, plus 2x equals 0. That's the second time I've done that today. And I think this factors. Whoops. The characteristic equation will factor once I write it down. But I gotta not forget to do that. So we have what? R squared plus 3r plus 2 equals 0. This factors. R plus 2 times R plus 1. So our characteristic roots are negative 2 and negative 1. Again, this is overdamped. And we start off with some constant c1 e to the negative 2t plus some constant c2 e to the negative t. We're going to find the derivative and then use our initial conditions to figure out our actual solution. So minus 2 c1 e to the negative 2t minus c2 e to the negative t. We'll use our initial conditions here. X of 0 is 0. So that means 0 is equal to c1 plus c2. And x prime of 0 is negative 2. So negative 2 is equal to negative 2c1 minus c2. Once again, this one sort of works out nicely if we just add these equations together because the c2's will cancel each other out. So we end up with negative 2 is equal to negative c1, or c1 equals 2. And if c1 is equal to 2, that means that c2 is equal to negative 2, using that top equation. And so that gives us our function. So 2 e to the negative 2t minus 2 e to the negative t is our function. We could take a look. I've got to adjust my window a little bit. So it was given, it started at equilibrium, but it was given an initial downward velocity, so I think that displacement graph kind of makes sense, and it's overdamped, so it's not kind of going back and forth. It reaches equilibrium and stays there pretty quickly. Questions? Okay. So I got a bunch of questions, like on like Monday and yesterday about the assignment that you're turning in today. So I thought it'd be a good idea to take questions that you have if there are particular problems that you want to talk about. And in the absence of questions, kind of give you time to kind of just work on finishing that up. So I'll throw it out to you guys to see what questions you all have. If you have the assignment finished, then you don't need to stay, but if there's some problems that you're stuck on or haven't had a chance to kind of start working on, hopefully we've gotten at least a start on some of them. Some of them are a bit involved, so I'm all ears to if you have any questions.
Can you go over number 4 a little bit?
Which one?
For 4.
4, yeah. So, let me just find it.
I twisted myself up on Dawn's.
Oh, you know what? I've got the practice, so hold on. Let me bring it up on Canvas.
I didn't even have a moment to look at him. The first like few were fine. It's kind of
I was so fun until the end because pieces are missing.
It's always a puzzle.
So for that one, hold on, I'm just going to grab a pen and write down a note here. So it's x double prime plus 4x prime plus 4x equals 2 plus t squared. Okay. So when we solve these, we always start with the homogeneous solution, right? So the characteristic equation for the homogeneous equation looks like this, right? R squared plus 4r plus 4. And what did you find for the characteristic roots?
Yes.
Oh, that's as far as I got on that one so far.
Okay, so we want to solve this quadratic. What are different ways we have to solve a quadratic? We've got like 2 or 3 methods at our disposal.
Like your A is over here, and my your B equals C is actually this. And then negative, I should know about the negative here, because it'll wash out at the same time.
So what are different options we have for solving a quadratic? Like just describing the techniques.
I've got a quadratic formula. You can break it apart and then take the square the middle, half the middle.
Right, so we can either use the quadratic formula or we could factor it or we could complete the square. Either one of those will work here. Does it factor?
Yeah.
How does it factor?
R plus 2 on each of those.
Mm-hmm. Great. So we have a repeated root here, right? So r equals -2. There's only one repeated root. That means that our homogeneous solution is some constant e to the minus 2t plus some constant e to the minus 2t times t. Or sometimes people write it as like factoring out the e to the minus 2t, so we have the linear c1 plus c2t times e to the minus 2t. But that's sort of that's where we have to start, right, with our homogeneous.
Yeah.
Okay, so then, you know, they tell us right in the problem we're going to find the general, which is the homogeneous plus the particular. What do we have to look to help us get the particular?
We've got the table on the notepad you gave us.
Yep. And if we look at that table, what does it tell us? Like, how do we start?
You look at just what this is. Wouldn't this just be an exponential?
No, because what we need to do is look at the forcing function, right? We're going to look at the function on the other side of the equation. That's what we turn to help us figure out where we start when we set up the particular.
So it's minus 0.5 theta. 2.5 C1 minus 0.5 theta. That's what we had, right?
Isn't the forcing function just -2, so that'd be a polynomial degree?
The forcing function isn't -2. The forcing function is the function that's on the other side. It's what I've highlighted here, right? There's the function on the other side of the equation. If it's equal to 0, the forcing function is 0, it's homogeneous. Otherwise, when we have a non-zero forcing function, then we have to find out what our particular is.
Yeah, isn't that the first one?
So if our forcing function is 2 plus t squared, it's a quadratic.
Final 0 on number 6.
Then how do we start?
Yeah,
Like,
I did that.
what form does the particular function, the particular solution take on?
That's for the, so that'd be 2a plus t squared.
So it'll be a polynomial of that same degree, right? So we're looking at this row here of that table. So if we're starting with a polynomial of degree n, if our forcing function is a polynomial of degree n, our particular is a polynomial, a generic polynomial of the same degree. So we're starting with a polynomial of degree 2 here, 2 plus t squared. So we need a generic degree 2 polynomial. So that's a t squared plus bt plus c. And once we know what basic form our particular is going to take on, where do we go from there? We need to find a, b, and c. So how do we do that?
I think it was on magnitude there. That's supposed to be root, right? R is supposed to be root. I think it's root, yeah.
Or just take the derivative.
Yeah. Yep, we need to take the derivative. In fact, we need to find the derivative and the second derivative, because what we're going to do is find those derivatives and then plug them in and put them into this original given equation up here, and then figure out what a, b, and c have to be in order to make that equation true. So if that's xp, then xp prime, what do we get there?
2a t plus b.
Mm-hmm. And what about the second derivative?
2a.
Mm-hmm. Great. So now, take your equation, x double prime plus 4x prime plus 4x equals 2 plus t squared. And now you're just going to substitute. Right, so this is going to go in for this. This is going to go in for this. And this will go in for this. Don't forget to also multiply by 4. But then you'll have an equation, and this is where we use that method of undetermined coefficients, right? Whoops, we compare the coefficients on the different terms, powers of t, to help us find a, b, and c.